Okay, the learning objectives for today, we're going to review how elements combine to form compounds and look at the names of some typical chemical compounds and what the rules are there. Calculating the molar mass of a compound, determining the percent mass given the chemical formula, and understanding the relationship between the empirical and the molecular formula. What we're not going to do, we're not going to go into all the naming conventions. Given the number of things we have to do in the class and the ability to look things up on the computer, I'm not going to force you to learn all the names. You'll generally learn them in the context of classes you're doing. It's useful to know them because if you're reading something in a textbook, you don't have to look up what the chemical formula and the name is. So we're not going to go into this, and I'm not going to have you memorize names. We're focusing on chemical principles in the class. So generally on an exam, I'll give you the chemical formula rather than tell you the name and have to guess the chemical formula. So it's useful to review it so it's in your mind. So you know there's a difference between perchlorates and chlorates and chlorites, that you know there is a difference, but actually memorizing which one has which number of oxygens, we're not going to do. So molecules and compounds. In the previous chapters, we mostly talked about elements. Yeah, 92 naturally occurring elements. It's kind of interesting, but much more interesting are the astronomical number of compounds, 10 to the 60th to 10 to the 80th or more, depending on how you count them, the different that are chemical combinations of elements. So how do elements combine to make compounds? So this is really going to be one of the core parts of the text, but core parts of the semester. But getting into this just basically, there's two types of ways that elements will stick together to make compounds that are homogeneous at a macroscopic level. One is ionic bonds. So if you have sodium and chlorine, sodium loses an electron and it becomes a positive ion. Chlorine likes to gain an electron to become a negatively charged anion. And because they're positively and negatively charged, they can form this crystal lattice and clump together. And they're quite stable together at room temperature and pressure. Of course, you can make them go apart by putting them in water, so it's not completely stable. But it's a commonly occurring pure compound that you can have. So that's one way, is that the elements combined by forming ions and just gluing together by electrostatics. So that's an interesting category that's useful. More common are covalent bonds. And we know that if you look at atoms, here we're looking at hydrogen with one proton and one electron. And so then generally, we have an electron cloud around the proton. And a chemical covalent bond occurs when two atoms, in this case, two hydrogens, rather than having the electrons just orbiting one, the electrons start orbiting or surrounding both of the atoms. And so that sharing of electrons is a covalent bond. So that is a major way, that perhaps the most common way that elements form compounds. We can represent covalent compounds in a number of different ways, and each of these different ways have advantages and disadvantages. So if I'm dealing with methane, I could say the molecular formula is CH4. And that tells me some of the information I need to know. For example, it has one carbon and 4 hydrogen. Good. And for a lot of things like stoichiometry, that's all you need to know. A second way of representing it is the structural formula, where what you do is you draw lines that represent the bonds. So here, it turns out that for methane, you actually have a central carbon with 4 hydrogens. We'll talk about why that's the case later, but a central carbon with 4 hydrogens. So the structural formula just shows where the bonds are. Double, triple bonds, we'll get into that later, but it shows where the bonds are localized, which atoms they connect. The ball and stick model adds a little bit more. It describes the geometry in space. And for some problems, the geometry in space is fairly important to know. The structural formula doesn't contain that information. So the ball and stick model says that, okay, these 4 hydrogens are actually equally spaced in 3-dimensional space around the central carbon. We knew that the carbon was central from the structural model, but we didn't really have information about where they're arranged in 3D space. The structural formula is written in 2D. The ball and stick model is in 3D. And finally, we have a space filling model. And what that adds additionally is the ball and stick model shows where the nuclei are, but the space filling model shows roughly, and it's roughly because it's an electron cloud that has some probability there, roughly where the electrons are. And that gives you a much better sense, if you're looking at a liquid, if you're drawing a three-dimensional picture of this in space, so you're trying to see how a liquid fills space, or you're trying to understand how a drug binds to a protein receptor, then the space filling model gives you a lot better sense of exactly how they're interacting. So those are the four major ways that we would represent covalent compounds, each of which are good for different reasons. If you're just doing stoichiometry, having to draw space filling models is pretty silly. So different compounds in different ways. So they can get much more complicated, and we'll get into that a lot more. Here we've got names of compounds. That is one way to represent a compound. If you give the name, that the person knows what the name means, that's enough to tell you what the molecular formula is. The empirical formula, we'll get into that a little bit more later today. The molecular formula, as we said, the structural formula. In this case, you start to see double bonds and triple bonds, ball and stick model, and space filling model. And as you can see, there's a lot of information in the structural models and in the space filling models that are not the molecular formula. So which representation do we use? It really depends on what you are trying to do at the time. So a little bit on representation of molecules.